So yeah, multiple regression. You've all done multiple regression at some point in time. I figured this is a nice, it's kind of a refresher topic, but also it's a really kind of critical modeling tool you use in organizations if you're trying to predict some outcome and you have multiple predictors. So multiple regression is also kind of a framework from which you can build all sorts of other predictive models. So whether it be logistic regression, multi-level modeling, there's all sorts of extensions to multiple regression. A lot of the concepts still apply. Yeah, so the general idea of multiple regression is that you have some sort of numeric outcome variable and one or more predictive variables, and you're trying to, I guess, predict, explain that outcome measure. There are many classic examples in organizational psychology that we could think about. Predicting job performance in a selection context. You might want to know how to weight your personality measures, your ability measures, your interview. If you had some data where you'd measured all those predictors and you had a measure of job performance, you could put together a regression equation and that would tell you how to weight each of those predictors, as well as give you an idea of whether they are actually predicting and to what extent. So yeah, it definitely comes up a lot in selection and recruitment. You could use it to understand, often they do things like driver analysis in market research, where they measure a bunch of characteristics of some consumers and they want to predict, I don't know, brand loyalty or purchasing behavior, and they want to look at sort of how much you like a product, your opinions about it, your demographics, and so on. So yeah, all sorts of domains, multiple regression is a tool, and possibly in a thesis it could be a tool where has anyone almost got that in their mind that that's what they're going to do, some sort of regression-based predictive model of something? Yes, yeah. I mean, it's pretty standard stuff. I guess the main thing that I was going to, when we get to the exercise today, is really getting you thinking about some of the preliminaries around multiple regression. So how do you code up your variables so that they're meaningful, they're on a nice scale? How do you deal with categorical variables? How do you create variables that are interesting? Okay, so this is just an overview of multiple regression process. Obviously, you've got to convert your research question into some sort of regression model, or perhaps a set of models you want to compare. You've got to ensure that you have a decent sample size and work through a whole range of assumption issues. Once you've got a model, you can get estimates of how well you're predicting, either the overall regression equations or the role of each individual predictor in terms of regression coefficients. And yeah, integrate that back into the research question. A very general distinction that's worth keeping in mind is, what are you trying to do with this regression model? Is it about pure prediction, or is it about explanation, or some sort of maybe are you trying to sort of have some quasi-causal assignment to those predictors? Just to clarify that distinction, if your pure purpose is just to get a good prediction, you just want to know something about something you don't know, then it doesn't really matter what predictors you throw in as long as they predict. In a lot of industry settings, that's what they're trying to do. For example, if you're trying to develop a selection and recruitment tool, your main goal might be to predict job performance or lack of turnover or something like that. And exactly how the predictors work might be more secondary if it's purely for an applied model. And you also see this in contexts like you might encounter when you're out there in the world, when they're trying to predict who's going to default on a loan, or who's going to, how many people are going to attend an event tomorrow, how many customers you're going to have in a week, all those kind of contexts. It's often about just getting a number that is accurate in predicting. And exactly how you get that prediction, well, that's important as a process so that you've got a good model, but it's all about the prediction. In contrast, if you're doing research in psychology, you're often more interested in the underlying model and the causal processes. And in that case, you often have to think a lot more about what variables you throw in. A nice example of this, just to highlight a pet peeve I have in research, is you'll often see that they put self-efficacy in as a predictor of, say, job performance or task performance. People heard of this concept of self-efficacy? It's your belief that you will be effective. Or sometimes it's domain-specific. Your belief that you will do well at some task. I think Bandura or someone like that said, well, self-efficacy predicts performance. And if you do regression equations or correlations, you'll see that self-efficacy does predict performance. Of course, the question is, that there may be prediction, but is there kind of a causal effect? Because there's another theory that says the reason why people believe that they can achieve is because they have some self-awareness about whether they actually will achieve or not. And therefore, it's really underlying skill is explaining both self-efficacy and performance. So yeah, sometimes you get these weird representations of self-efficacy. If you put in skill as well, then skill will predict performance, and self-efficacy can sometimes even be negative because what's left after you take out skill is just some sort of biased self-impression. Anyway, the general point there is that if you're trying to put in predictors, you need to think about whether you're trying to assign some sort of causal interpretation, or are these kind of just predictors for their own sake? Another example would be in the job satisfaction space. I've seen a lot of regression models based on climate surveys where they want to predict engagement or job satisfaction. And so they put in a whole pile of other climate variables like role clarity and commitment and any number of those kind of variables. And they all correlate massively with job satisfaction and engagement. They often try and see which one's doing the best prediction or which one's driving engagement. However, the issue is that there's like this massive kind of global job satisfaction effect that's hanging over all these variables. A general positivity that's often hanging over all those climate kind of variables, which may be driving a lot of the correlations that we're seeing. So you get weird things like the variables that are almost the same construct as engagement being the best predictors of engagement. And so is that really interesting to say that, for example, commitment predicts engagement when, well, engagement kind of is commitment? So there's a bit of an issue there when you're developing your models about, you know, are you trying to tease out some sort of conceptual processes, or are you just trying to do a pure prediction equation? And if you're doing it for explanation, then I think you need to think a bit more about what predictors you put in. Does that relate to anyone, or does anyone relate to that distinction in terms of their regression models they've done in the past, or they're thinking about for their thesis, or whatever, that you're trying to say something about the process or the role of different variables?
So we want to say you have an engagement measure, you want it to correlate with the outcomes that you want to see as a result of engagement in the organisation, but if it correlates too high, you really just, the outcome obviously isn't a separate enough outcome.
Yeah.
Does that make sense?
Yeah. I mean, I think particularly with like self-rated psychological variables, there's this fear that, particularly like in climate surveys, that there's something general that's explaining all this stuff, like a general job satisfaction dimension that's driving a lot of these correlations. Whereas, for example, if you're interested in whether role clarity predicted job satisfaction, you might want to actually objectively measure the degree to which someone's role is clear and see whether manipulations of that actually improve job satisfaction. Of course, that's a lot harder than just administering a survey, which is why people just administer surveys. But yeah, I think that's a good example. Okay, so there's that distinction between prediction and explanation. You can also think about the concept of parsimony, about how many predictors you want to have in your model. Often you want to have better explanation, but you don't want to throw in too many redundant predictors. You want to have a nice, concise model that clarifies phenomena. Just as with what we've seen with EFA, CFA sort of thing, there is a sort of orientation when it comes to running models. You can be exploratory, where you're very open to what predictors you're putting in and trying to find a model that is effective. Alternatively, you can be more confirmatory and saying, look, I want to test this model and see how well it predicts. Or you might have a few explicit competing models and you want to compare those. A lot of my research using regression tends to be a few explicit models that we're testing and comparing. For example, I've done a fair bit of research on comparing the big five with facet level models of personality. And so I do a lot of comparisons of how well does the 5-factor model predict, say, job satisfaction or workplace performance versus a 30-facet model of personality. So it's an explicit, it's kind of a confirmatory approach. We want to know how well does the big five predict, how well does this predict, and that has a nice mapping onto theory and ideas about how we should represent personality. Other times you might have other kind of explicit comparisons of interest. You might have your 3 main effects and you want to test whether there's a bunch of interactions over the top. So you test the main effects and some interactions. Or you might have some model where you've got your demographic predictors and you want to see whether a set of psychological variables predict over and above some demographics and compare those two models. So a lot of multiple regression, I think, for research is often about comparing interesting models from a theoretical perspective. Whereas applied research can often be a bit more predictive in approach. So that's what a regression equation looks like. Essentially, we're saying we have an outcome measure, y, and each person, I, has a score on that outcome measure. So that could be job performance for person I. How many widgets did they produce this week? How many sales did they make? How much product did they sell? So you've got a score for every person, and you're trying to explain that. You're trying to explain that job performance score or that job satisfaction quantity. And the idea is that everybody's score is due to some function of the predictors and some error. So say that was the big five. We've got 5 predictors, our x's. We've got x1, which is, say, neuroticism, extroversion, all the way up to agreeableness or something. We're saying that we can have an equation with coefficients, a constant, plus some weight of each of the predictors. And so if we apply that equation after getting these coefficients, we get an expected or predicted amount for each person, their predicted job performance. So that's what this beta 0 to beta p bit is doing. We're saying we've got p predictors, and that's our prediction equation. And we could slot in a person's score for each x, multiply it by these coefficients that we've obtained, and we get a prediction. And so we put it all in. We predicted that a person produced 20 widgets this week, but they actually produced 25. So our prediction will not be perfect, as we know. So we've got a prediction. It's not perfect, and that's what the EI represents, the deviation from prediction or the error. So yeah, we've got a prediction bit, and we've got a residual or error bit. The idea is that in theory, we're saying that the errors normally distributed with a mean of 0 and some sort of variance. And altogether, that really defines our equation. We've got our coefficients and our error variance, and that uniquely defines our regression equation. This bit is just decomposing it to say that we've got our prediction, our y hats, and that the observed scores equal our prediction plus an error. So in the case of someone who produced 25 widgets, we predicted they produced 20 plus the residual of 5. That's our prediction. Okay. So these coefficients, these B or beta values, this is what tells us what the effect of a given predictor is on the outcome. We can have unstandardized and standardized. In psychology, we often like standardized coefficients. But yeah, unstandardized coefficients have the interpretation. It's the expected change in y, the outcome, for a 1-unit change in the predictor of interest, holding all other variables constant. And that's in whatever metric the variable is in. So it could be a 1-unit score on a Big 5 measure, for example, or it could be $1 more if that was an income measure, or one whatever. Generally, when we're interpreting it, we look to see whether it's positive or negative. So is more openness leading to more job performance, or if it was negative, then it would say more openness leads to worse job performance. We're also looking at the degree of relationship. So how strong or how large is this coefficient? Unstandardized coefficients are really nice if you can get the metrics to be meaningful, which often takes a bit of work in psychology. Often our metrics are just sort of kind of arbitrary psychological scales, and they're not that meaningful. But variables like income, for example, is quite a meaningful scale. It's quite intuitive. $1. We understand what $1 means, so therefore we could say, as you pay someone $1 more, you get, or say you pay someone $1,000 more, then you get this much more in performance. But if the metrics are not very intuitive, which is the case with probably a lot of psychological measures, we often use standardized scales to make it more intuitive. So this is for me the idea that you can convert your predictors and dependent variables to z-scores. So the mean is 0, the standard deviation is 1. You could do this manually, literally. You could literally z-score all your variables and run a regression, and your unstandardized coefficients would actually be standardized coefficients. But SPSS saves you the hassle, and they give you that standardized regression coefficient. So that's 1 unit now is 1 standard deviation. So for a 1 standard deviation increase in the IV, you get whatever your coefficient, that many standard deviations increase on the DV, holding all other variables constant. There's a whole pile of things in a regression that you could focus on. Probably the big ones are estimates of variance explained. So your say R squared or adjusted R squared. This is the proportion of the variance in the outcome measure that is explained by your regression equation. R squared is the estimate of the value in the sample. Adjusted R squared estimates how it would operate in the population if you were to, say, get a much larger sample size. It's an estimate of population R squared. This is probably the fairer estimate to report. Then you've got your coefficients and also various correlations that we'll talk about that can be useful. A common issue that you have to deal with is to work out, what what predictors are more important. You know, for example, if you're doing a survey analysis and you're trying to say what are the key drivers of job satisfaction, well, although I just said that it's probably not a good idea to do key driver analysis and just assume that correlations are good. But the point is that you can look at a range of indicators to decide which predictors are more or less important. One approach is to look at the standardized betas, because they standardize everything onto a common metric, and that can guide you. So, I did a paper once where we were looking at how the big five predicted life satisfaction. We looked at the standardized betas and we saw that yes, neuroticism was the biggest coefficient. Then there was a bit of extroversion, and then I think there was a tiny bit of a few other things as well. But by looking at the standardized betas, we were able to kind of clearly see what was the stronger predictor and what were the sort of smaller predictors. A related or what approach that will often give you similar answers is to look at semi-partial correlations. I think that's probably slightly more defensible, and we'll look at some examples of that. And one approach I probably wouldn't recommend doing is what's called stepwise regression, where you just let an algorithm to decide which predictors to include in your model. That can be a bit arbitrary. Hierarchical, no. No. Stepwise, I'll explain in a bit. The general idea is you can either do it forward or backwards, but you either like throw in all 5 predictors, and if any one of them is not significant, it throws it out, and it keeps throwing them out until throwing something out would make the model worse. Or alternatively, you start with no predictors and it adds one, and keeps going until adding something doesn't improve it. So it's very data-driven. It might be okay if you're interested purely in prediction, but in psychology we're often testing formal models of things, and it's probably not the best option. But you could argue that predictors that are retained are in some way important, I guess. And people do that in the literature, but I'd argue it's not so good. You can also quantify the uncertainty of your coefficients, like your regression coefficients, with confidence intervals. So that can be nice to get a sense of what are the plausible range of values. But yeah, I mentioned semi-partial correlations before. In general, if you look at the output of SPSS, you'll get 3 types of correlation. One is zero order. That's just a fancy name for what you're familiar with already. That's just your bivariate correlation. So that can be a quite interesting contrast, I think, to look at the just straight bivariate correlation between a predictor and the outcome. What you'll often see is you might have a lot of meaningful correlations between your predictors and an outcome, but when you put it in a model, one of those predictors is so much more important that it kind of swamps out the others, and the others will kind of disappear in the regression equation. I was recently working on a paper predicting health behavior and psychological distress, and there's this model of personality of health behaviors that says, to be honest, it's kind of a recreation of extroversion and neuroticism, but they call it social inhibition and negative affect. It's this theory called type D personality. I don't know if anyone's encountered it, and so social inhibition is kind of like shyness, and negative affect is basically neuroticism reinvented. And so when they both correlate, if you're socially inhibited and you have negative affect, you tend to experience more physical symptoms, you tend to engage in fewer positive health behaviors. But when you put this in a regression, negative affect is the main thing, and it sort of swamps out the social inhibition effect. And so one could argue that it's the nugget, or the real effect is the negative affect, and then the only reason that social inhibition is predicting these behaviours is the extent to which it shares variance with negative affect. So that's an example where you will see zero order correlations at the bivariate level, but the beta coefficients, and also what we'll talk about now, the semi-partial, will tell you what's the kind of more the unique or role of each of the predictors. So the semi-partial coefficient will tell you to what extent that predictor adds explanation over and above the other predictors. Essentially, it's saying controlling for the other predictors, to what extent does it correlate, or if you square it, to what extent does it explain, what percentage of variance does it explain uniquely? I think the semi-partial can be a nice one to report to give you a flavour of what's the unique contribution of this predictor over and above the others. Partial's a bit different. It sort of adjusts for the DV as well, but probably not worth focusing as much on that. Here's a little summary table of some of the, assumptions or kind of issues you might need to think about in your regression equations. Certainly sample size is a big one. You want to make sure you've got enough people to get reasonable estimates. We'll talk a bit about that. Multicollinearity refers to correlations between the predictors. At a basic level, your correlations of 0.4, 0.5, 0.6 between predictors, they don't matter so much. They may make it harder to determine which variable is doing the unique prediction, but they're not the end of the world. It's really when you get really large correlations where your regression coefficients might start doing crazy things. And you may need to leave one of the predictors out, or perhaps combine a couple of them together. Multiple regression assumes linearity of relationships, which most of the time that's the case in psychology. You know that more of one variable means more of the other. If you do want to get into nonlinear relationships, there are things like polynomial regression where you can square variables, particularly variables like age. Age often has quadratic effects. Effects of time, that's often nonlinear. And then we've got outliers we need to be careful of, and a few other things about residuals like homogeneity, variance, and normality. In terms of sample size rules of thumb, this would be my very, if you didn't think about anything else, that would be my very rough rule of thumb. For the kinds of things that we do in org psych, that if you've got 100, you can probably present at a conference. If you've got 200, you might be able to get into a journal if you've got really interesting variables, and 400, it's looking pretty defensible. That's a really rough rule of thumb, of course. And a lot of it depends on what you're doing, how many predictors you have. If you've got more predictors, then you're probably going to want to have a bigger sample size. If it's a well-studied relationship, then you're probably more interested in getting a precise estimate rather than working out whether an effect's there or not. So in that case, definitely more is better. But yeah, I don't know. Often sample size is determined a lot by just the constraints of your research and how many you can actually get feasibly and all those sorts of other issues. But yeah, I don't know. Do people have any kind of issues or concerns with sample size in their thesis, or they want to talk about that sort of stuff? G power is pretty good, but that can give you power analyses that are useful. But often you will have multiple kind of things you're doing with your regressions. You'll be checking whether an interaction term predicts over and above main effects. You'll be looking at whether, whether a whole range of coefficients is significant, looking at the overall R squared, comparing models. So it is quite tricky. Each of those kind of questions may have will have different power. So often you'll have plenty of power for the overall model, but maybe if you're assuming like interaction terms, they're often very small if they exist at all. in which case you may need 800 or 1,000 people to have a reasonable shot at finding an interaction effect in a survey. Things like that. So depends a bit on your purpose. So yeah, let's have a quick look at an example. This one's looking at how well 3 ability tests and a knowledge test predicted some typing speed, which is just a data set I had from my thesis. So it wasn't a focal question of interest. So we've got these variables. It's good to take note of the metric so that we can interpret the unstandardized coefficients. So typing speeds is in words per minute. That's pretty intuitive, 29 words per minute. I don't know what people's typing speed is in this room, but you know, a good speed might be 60. 30 is kind of adequate, maybe. All the ability measures have been Z-scored already. They're all standardized already. And the knowledge test is out of 100%, or it's a proportion. So people got 46% of some knowledge test correct. That's a little look at the individual predictors. Not perfectly normally distributed, but not too bad. We can have a look at the zero-order correlations between our outcome measure, typing speed, and the predictors. And we can sort of see that there's the correlations with everything. More ability, better typing speed. More knowledge, better typing speed. Perhaps it's this perceptual speed and maybe the knowledge test that's the best predictors, but they're fairly even. And there's not huge multicollinearity here. We're getting some small intercorrelations between some of the ability to test, but it's nothing crazy. In terms of the overall model, we've explained 31% of variance in the sample, or perhaps more realistically, we've explained 28%, you could say, in the population. Well, that's our estimate. And that's a significant overall regression model. So overall, we're explaining significantly more than 0 variance. So, not too bad. In terms of a regression equation, we could predict someone's typing speed as 22 words per minute plus 1 unit times their general ability plus 3.8 times their perceptual speed ability plus 0.36 of their psychomotor plus 14 times their proportion correct. And you could apply that to anyone's data and get a prediction of their typing speed. In terms of interpreting coefficients, I guess we're saying that if you increase your general ability by 1 unit, you would generally be typing 1 word per minute faster. Or if your perceptual speed was 1 unit more, like 1 standard deviation, you'd be 3.8 units faster. A movement from 0 to 1 on this would be from 0% correct to 100% correct. So that would be a difference in, say, 14 words per minute. Not a massively interesting application, but I think it's analogous to a whole range of things you could do in a selection and recruitment context. We can also see which predictors are statistically significant, and that was just the perceptual speed and the knowledge test. If we wanted to evaluate how important these predictors were, so I'll just go back to here, we could look at the standardized coefficients, which suggests that perceptual speed and knowledge are the 2 key predictors. So they're both fairly substantial. Or we could look at the semi-partial, which strangely SPSS calls part. And yeah, that also seems to suggest that perceptual speed and total knowledge are the largest semi-partial correlations. So that's sort of an example where these 2 predictors were present, general ability and psychomotor were present in the 0 order correlations, but after controlling for these other predictors, they kind of disappeared in the equation. You can also get a whole range of outlier statistics, and there's some rules of thumb there for diagnosing that, and you can save those residuals and flag problematic cases that might have some issue. But I guess you want to be thinking about, is this a case that I want to be modeling, or is it just something weird going on and we want to remove that from the model?
When we're then going on to like making a prediction based on particular variables, would you use those ones that weren't very predictive, like just weight them much less, or would you just cut them out altogether?
I guess it depends. So you're saying like you're in a selection and recruitment context, you're trying to develop a regression equation to weight your tests, and you're trying to work out what's a good model.
Yeah, well, like say that like 70% of it is predicted by personality or something, or some abstract reasoning test, but then like 2% was predicted, like it doesn't matter then, like you just cut that out.
Yeah, I mean, I guess.
So then it's just a logical decision based on whatever you think. Like, yeah. But then it depends if the extra 5 is like by completing an extra hour of an exam, or like what's involved in getting that 5%.
Yeah, I think you're getting to the where the stats meets the practical reality of, like what's the gain in predictive validity versus what's the cost in running this test, or is that sort of, I mean, if you're developing a selection system, you definitely want to think about cost, time, all those kinds of things. So maybe you would drop, if you wanted to make it a bit more concise, drop the measures that don't predict. You can also get plots of the residuals to see whether it's roughly normal. Here it's not perfect, but it's not too bad. You can get a plot of the predicted values. These are standardized predicted values. So these are people who are predicted to have, on the right, very fast typing speeds, and on the left, very low typing speeds. And plot that against the residuals. So that's whether the person had a higher typing speed than was predicted, if you're above the line, or a lower typing speed than predicted, below the line. You sort of want to see just a random scatter, really. If there's a systematic pattern, like a quadratic pattern, or maybe some flaring, it would suggest that maybe homogeneity variance isn't satisfied. This looks fairly random, so it's okay. You can check linearity with normal scatter plots of the predictors and the outcomes, or you can do these partial correlation plots to sort of check whether it looks roughly linear. This has got a sort of localized fit measure overlaid. They generally look okay, I think. I mean, this localized fit's a bit over sensitive, I think, in terms of highlighting things. In most contexts, you also have some theoretical knowledge about whether things should be linear or not. And certainly if you've got no relationship at all, then you can get all sorts of strange patterns. So that's an example of a multiple regression, the general flow. Probably one of the things that I do most often when writing papers with regressions is hierarchical regression. So this is basically just comparing a few different models and seeing, asking questions like, well, if I add this, does this improve things? Or how does this model compare to that model? With this paper we're writing at the moment, we predicted health behavior from a couple of personality variables, as well as some illness groups. And we did hierarchical regression in the sense that we had some main effects models, but we also looked at to see whether our personality variables interacted. So we did that in a separate block to see whether that predicted over and above. Or we interacted our personality variables with illness status to see whether those interactions improved the model. So we had these, what you call hierarchical regressions, where you have a base model and then you add some predictors and see whether they, say, add explanation over and above another set. I think that's generally a nice way of structuring theoretical questions, like, how much additional variance does this set of variables explain over and above? Or do we need these interactions? Do we need this set of predictors at all? So it's often a nice way of organising a paper around sets of predictors and what do they add over and above other sets. So in general, you'll get an R-squared for the initial model and the updated model, as well as an estimate of how much the incremental prediction, how much incremental prediction you got from the second set of variables, as well as a test of whether that was statistically significant. And often that's used to determine whether you should include interactions or include particular predictor sets, or you might just want to estimate incremental prediction. So for example, you could put personality in the first block and you want to see how much intelligence predicts over and above personality. Or if you were a cynic about emotional intelligence, you might put personality and intelligence in the first block and see whether emotional intelligence could explain over and above the more traditional measures. So they're kind of applications. I think I've said enough about stepwise regression. In general, I'd stay away from it, but that's probably my psychological theoretical orientation coming across. In applied settings where you're really interested in prediction, they'd use a lot more data-driven approaches to selecting predictors and developing prediction equations. And stepwise regression is just one of many tools that they use. And probably the main thing there, if you are doing a purely predictive model, is to have what they call a cross-validation sample. So you optimize your model in your exploratory sample, and then you apply it in a cross-validation sample to see how well it performs. But most of the time in theory and in psychology, we're doing more theoretically driven approaches. Just a quick aside here about categorical predictors. If you do have categorical predictors, which we often do, the simplest case is binary. You want to put gender in a regression. How often we love age and gender in psychology, so we're always putting gender in a regression. The key thing to do is probably to code it 0 and 1. That'll make everything nice and clear. And don't call it gender in your regression table. Call it whatever the 1 is. So if you code 0 female, 1 is male, call the variable male. Or if you do call it gender, make sure you've got a little thing in your table and a note at the bottom that says gender coded 0 equals male, 1 equals female. Or actually, I just flipped that around. Female equals 0, male equals 1. Yeah, because that coefficient is going to mean the effect of being whatever the 1 is. If you've got 3 or more categories, there are a range of ways you can code categorical, but the most common is dummy coding. And generally, you'll end up with k minus 1, where k is the number of categories, dummy variables. So if you had 3 grades, fail, pass, honours, you could code that into 2 dummy variables. One category would be the reference category, which is defined by when both dummies are 0. And each dummy variable would represent the effect of being that category relative to the reference category. It's a bit of a pain in SPSS. I have to say, categorical variables in SPSS, you have to manually create these things, so it's a bit of a pain. R does it it'll just automatically do dummy coding on any categorical variable, which is a nice feature of regression in R. But yeah, otherwise, pretty much in SPSS, you've got to put a bit of syntax to say, compute dummy 1, if ons equals 1, dummy 1 equals 1, or something like that. Should be able to find syntax out there, but it's a bit of a chore. As an aside, it also, I guess, highlights how t-tests and ANOVAs really are just regression. It's all just the linear model, in that you can have categorical predictors in regression. Yeah.